The work substantiates the feasibility of creating an adsorption technology with controlled activation of the adsorbent for the removal of sulfur dioxide, nitrogen oxides, and carbon from the flue gases of coal-fired power plants. The national report on the state of the environment in Ukraine in 2020 shows that 3.8 tons of pollutants were present per square kilometer of the country's territory. On Figure 2 presented the main chemical components entering the atmospheric air from stationary sources, substances in the form of suspended solid particles 248.9 thousand tons or 11.1% of the total volume of pollutants, dioxide and other sulfur compounds 782.1 thousand tons or 34.9%, methane 429.1 thousand tons or 19.1%, nitrogen oxides 3.4 thousand tons or 0.50%, carbon monoxide 707.3 thousand tons or 31.5%. Almost 37.9% of pollution from stationary sources comes from the energy sector, mainly thermal power plants. Independent researchers also confirm the significant damage that flue gases from the coal-fired power plants cause to the environment. According to this report, Ukraine is one of the leaders in Europe in terms of atmospheric air pollution, with sulfur and nitrogen emissions emitted together with the flue gases of coal-fired power plants. Among the 30 coal-fired power plants in Europe that pollute sulfur dioxide the most, 20 belong to Ukraine. Ukraine ranks second in Europe in air pollution with nitrogen oxides. Ukraine produces 34% of its electricity consumption from 20 coal-fired power plants built before 1976, none of which have desulfurization equipment. Therefore, the task of cleaning flue gases of coal-fired power plants from sulfur, nitrogen, carbon oxides is extremely relevant in the European context. The analysis of the literature showed that when burning coal at thermal power plants, solid wastes are formed, ash and slag, and gaseous wastes, oxides of sulfur, nitrogen and carbon. At the same time, it is possible to create such a technological process when the solid emissions, ash will be mechanically activated and will absorb oxides of sulfur, nitrogen and carbon. The laboratory unit for researching the process of adsorption from flue gases under the conditions of mechanical activation is presented in Figure 3. Adsorption of nitrogen oxide, sulfur dioxide, and carbon monoxide was studied. Ash from burning coal and cellulites of various types were used as sorbents. Before the start of the experiment, the V1 tank is filled with a mixture of air, sulfur dioxide, nitrogen and carbon, which is analog of flue gases produced during the burning of coal at power plants in different modes. The obtained gas mixture enters adsorber from above. The adsorber is filled with sorbent and dispersing material. Gases from the adsorber enter the V2 receiver. Pumping of the gas mixture from V1 to V2 is carried out by the compressor, GC. The unit has two sampling points of the gas mixture for analysis, the initial mixture and final products. The content of oxides of nitrogen, sulfur and carbon is determined by a portable gas analyzer Oxy5M5H with an error of 5. The volume of the laboratory adsorber is 8 cubic centimeters. The capacity for gases is 50 liters. At a gas supply rate of 5 to 25 liters per hour. The duration of the experiment is 2 to 8 hours. Variable parameters during the experimental work were temperature, flow rate of the gas mixture, concentration of gases in the mixture, vibration frequency of the vibrating device. The degree of sorption and sorption capacity are highly dependent on temperature, intensity of activation, type of sorbent. The dependence of sorption efficiency and sorption capacity passes through maxima and is very similar to the dependence of the degree of transformation and the speed of chemical reactions on the frequency of mechanochemical activation in processes that take place using aerosol nanocatalysis technology. This indicates that sorbent activation is very similar in nature to catalyst activation. Figure 4 shows the effect of mechanical on the sorption capacity on the sorbent coal ash relative to sulfur dioxide. The presence of a maximum of the absorption capacity at an Ma density of 1.7 Hz and tendency to a second maximum at an Ma slightly higher than 8.0 Hz is observed. The dependence is described by equations on figure 4. The capacity achieved with the help of Ma adsorption is such that it provides effective purification from sulfur oxides or flue gases from the burning of energy grades of coal with an ash content of 30%. The use of Ma is able to increase the adsorption capacity of ash by 2.7 times at a temperature of 423 Kelvin degrees. It also allows to organize an industrial technology for removing sulfur oxide without cooling flue gases, which will significantly reduce energy costs on the scale of an industrial process. The use of ash from the burning of the same coal as a sorbent will allow reducing material costs on the scale of the industrial process. The process is able to provide 100% removal of sulfur dioxide when its content in flue gases is up to 450 ppm, a typical amount for flue gases from burning low-quality thermal coal with an excess of 1.25 air. At an adsorbent concentration of 16. In figure 5 shows the effect of Ma on the adsorption capacity of the same ash in relation to nitrogen oxides. The values are in the same ranges as for sulfur dioxide. The use of Ma is able to increase the adsorption capacity of ash in relation to nitrogen oxides by 2.1 times at a temperature of 423 kelvins and ensure 100% removal of nitrogen oxides from flue gases from the burning of thermal coal at a concentration of sorbent ash at the level of 20 grams per cubic meter of flue gases, which corresponds to the technological mode of combustion at industrial plants. This cleaning technology does not even require an additional amount of adsorbent. At an adsorbent concentration of 16 grams per cubic meter of flue gases. The presence of a maximum of the adsorption capacity at an intensity of Ma near 3.0 Hz and a tendency to a second maximum at an Ma above 8.0 Hz is observed. The dependence is described by equation on figure 5. The capacity achieved with the help of Ma adsorption is such that it provides effective cleaning of flue gases from the combustion of energy grades of coal with an ash content of 30% and nitrogen oxides content of up to 250 ppm from nitrogen oxides. In some modes of coal burning at thermal power plants, carbon monoxide formation is possible, so it is advisable to study the ability of ash to adsorb it as well. In figure 6 shows the influence of Ma on the adsorption capacity of ash in relation to monoxide of carbon, and the change in adsorption capacity from Ma is described by equation on figure 6. For carbon monoxide, the influence of Ma is practically noticeable. In the absence of Ma, it was not adsorbed at all under the experimental conditions. The use of Ma at the level of 1.2 Hz made it possible to increase the adsorption capacity of carbon monoxide by more than 5 times in comparison with other modes of Ma. Conclusions, figure 7.